Okay, to start the afternoon session, we have Sergei Gukov talking about new TQFTs from DAHA.
That's right. So first I want to start by thanking the organizers for organizing this. Thank you. And for all your hard work, especially David, and you worked really hard. Also for squeezing me in very time-constrained slots, and for many other things which you know. Right, so as for the talk, it will mostly be Blackboard, and I understand that there are some students in the audience from last week. So first 10 minutes and possibly last 10 minutes will be for you, entertaining, understandable, and everything else will be technical, and I'll explain why. Not in a computational sense, but in conceptual. Not in a computational sense, but in a conceptual way. So I'll make more comments on this later, but I want to start with some kind of entertainment that I would invoke maybe, I don't know, 15 years or so ago when I was young, like many of you in the audience. I would start the talk by asking some random member to give me a number. For example, then give me a number.
17.
17. Oh no, sorry, between 1 and 10.
1.7.
Integer.
7.
So it's actually interesting. For some reason, people always say 7. I have no idea what's happening. Anyway, so I'll then ask, okay, somebody else give me a knot with the 7 crossings. And I would promise for you to do a magic trick where in 10 minutes, I would give you Hovanov homology of that knot. So you give me the numbers, the audience is unpremeditated, so it will appear on the board in 10 minutes. And many in the audience actually know how to do the trick. For example, Alexei can perform it for you. If, again, students, you get lost throughout the talk and you want some entertainment, ask me how to do this or perform this magic trick live after or during the question session. So I'll be glad to do it. So I'm not going to walk you through, so pretend that there is a knot on the blackboard with, I don't know, crossing 7-3 or something like this, and we're trying to compute Hovanov homology. So I'll make the problem a little bit easier in the sense I'll pick a knot, I'll make it simple, but I'll make it complicated in the sense that I'll show you how to do this magic trick with categorifying color-Jones polynomial. So this is the knot, it's a simple trefoil knot. This is color-Jones. Yeah.
Is it true when the 7 is big enough, then your trick will not work? You will have to decide between two choices.
Well, ask me. I mean, it's a real trick. So ask me, but up to 10 crossings. Let's keep it reasonable.
Deliver.
Yeah. For example, you can in the question session ask me not I don't 942 or something. Huh?
They cannot be 15 crossings.
No. Beyond 10 it will be hard. No, then I don't. No.
But I'm saying it will be impossible.
Yeah, so using magic trick, of course, impossible, right? So, but the idea, so the trick, of course, is not about, and I'll try to explain, it's not about really getting the number. It's actually also useful if you want to have something concrete in front.
Just continue.
But there is a lesson in it, and actually that's why I'm performing kind of this.
Ivan is getting impatient, please.
Okay. So anyway, this is color-Jones, so a trefoil knot. So how do we categorify it? The idea is that we should produce vector space whose grade for the characteristic is this. It's a second symmetric, so this is what notation means here. And equivalently, if you think about Poincare polynomial, you want to restore variable t in every term such that if you set t minus 1, it becomes this. So how do we do it? So part of the trick is that, first of all, you go to extra dimension, in quotes. In a sense, you make the problem about SLN rather than SL2. So this is SLN version of this color-Jones polynomial, which also can be computed using the tools of previous century, so there is nothing complicated about it. And next you start paying a little bit attention how this answer depends on n. So n is the rank. And what I'm going to do next, and that's the next step in this magic trick, you plot this result on a piece of paper, which you grade on a two-dimensional grid where Q grading will be on this axis, and n dependence will be on the vertical axis. So if I see, for example, power for n plus 3, this is how this term depends on n, I put it in position 4 with respect to vertical grading and position 3 with respect to horizontal grading. So for example, it will probably be that one on top. So this one here, for example, is 2 and 2. It will be, or 2 minus 2, it will be this guy, and so on. So here there are some number of terms that become bullets on this two-dimensional
But what
plane.
happens if the m is small, like 2?
If n is 2, there are maybe some cancellations. So part of the trick to compute something for SL2, that's what we wanted. So the goal is to go from SL2 to SLN first and then specialize that. So part of the first step on the trick, do it for SLN. So actually this is advice I learned from Sir Michael. I used to visit him pretty much every year. And one of the pieces of wisdom that he taught me is, if you want to solve a problem, generalize it first. So this is exactly the first step. So second step, plotted, but again, we're not really making progress towards categorification, it's just reshuffling the answer. But this is part of it. So next goal is going to be to give this homological T grading to every term here, thinking about it in terms of kind of generator of homology. So a priori, it may be tough, but now we'll require two properties. We'll require that all terms but one can be canceled in this picture if you take the homology with respect to either this differential, which has A grading, meaning vertical grading, -1, Q grading, which is the next one, -2, which means it goes to the left, and it lowers the third grading, to which we had absolutely no access so far, -3. And then there is another differential like that, which increases Q grading by 1, so it goes in opposite direction, and changes homological grading by -1. The third slot in here is the grading we want to restore. That's homological T grading. So first thing, you may say, I don't even know if such thing can be consistent with all those bullet points, the dots on the diagram. If it's not, then you have to invent new ones, but again, somehow up to 10 crossings, it always works. So indeed, 15 crossing would require more tools from more sophisticated techniques. So this is just a point. And first of all, you notice that indeed, the whatever 9 points I had on this in this example can be indeed paired exactly like required, such that one term remains. So you have 4 pairs and 1 unpaired die. And then you notice that if you use the other one, also you can pair them perfectly, and there is only 1 unpaired die left. So now you can say, okay, let me use this property to restore the missing hidden variable with T grading or homological grading. Up to overall shift of grading of homology, we can declare that this has homological degree 0, and then this point should have homological degree, can you guess, from this property? 3, because differential lowers it by 3, so this, if this is 0, the next one has to be 3. I believe that's what's on the next slide, yes? So you do it perfectly. So what do we do now? So once we have this one, we can now start going, for example, to this point by using the other differential, and we know how much it changes the T grading, namely it lowers by 1, so 3 becomes 2. Now I can go to this point. So what will be homological degree of this guy?
5.
Perfect. So see, that's how you compute Hover-Not homology. You go, that becomes 4, and this becomes something else. So this is a kind of magic trick. Again, it's of course just entertainment, and it's an example of how to do these things quickly in 10 minutes if you really on a bus and everything is shaking and you want to scribble on a piece of paper. But there is a lesson here, so it's not just for computational thing, but for the lesson.
How did you know you have to, this graph is not connected, so
That's right.
there is no way to decide which is 2 and 2.
Right, so in color case, this is more interesting, so that's what I'm showing here. In uncolored case, there is a very simple rule. If you see several components, which are, for example, this would be 3, this would be 5, and the only thing, I'm teaching you this trick kind of in uncolored case, if there is something appearing in between, just average. It will be 4, and it will always work. Again, I didn't tell you that it has to be super intelligent. I promise that for any knot up to 10 crossings, you can reconstruct it on a board in less than 10 minutes.
What number is 4?
Well, he is asking a very good question. So if you have several components here, so how do I know that this diamond contributes with this degree? For example, this is 3 and 3. For this, I use actually something fairly sophisticated, some analogs of this, differentials in colored case, but in uncolored case, I'm just saying you don't have to know anything more, just average. If you have point here is 3 and 5, there'll be no more than 1 or 2 points here, and they always have degree 4. Just averaging will always work. Anyway, what does this illustrate, and actually where does it come from? So this trick is actually using a structure, so it's not about particular trick or computation, it's about the structure. And the structure is that there exists, that's what behind the hood here, is that there is a Homfly homology criteria defined Homfly polynomial. So when we generalize to arbitrary rank and use that as a leverage to stratify, grade everything by rank as well, that's actually what makes this thing work. And again, this naturally came out in my joint work with Schwartz and DAHA 15 years ago, and ironically, right at the time, when homology was first constructed and so on, Mike Hovanov had a very nice paper on SL3 in homology where he said, I don't believe in a triply graded homology categorifying the Homfly polynomial. Actually, that's what I just showed you. And therefore, we'll construct each homology in each degree one by one. So SL2, SL3, and so on and so forth. So I was young, untenured, not even a faculty at the time. So I was really scared to make a conjecture about something that should exist against the word of mathematician who already was fairly prominent at the time and constructed famous Hovanov homology. So, as we know now, luckily, Homfly PT homology does exist, and this structure, which this differential show you, exists in nature. It's a very rich, interesting structure. It's not just to do magic tricks, but it actually is trying to help you with understanding of the homology itself. And what I want to show you today is kind of analogous to this situation many years ago, where there is no safety net, that there is no nothing to compare to, or no end of the textbook where you can look what the right answer is. And it's kind of scary making the steps when there is nothing to compare to and there is no calculation. So the goal of today's lecture, that's one of the lessons, is to make step into unknown and try to explore something that barely exists at this point. So therefore, that's one lesson of the talk. Of course, concrete lesson also involves the differentials. We'll see some of them several times in various incarnations. So the name of this new gadget that I'm going to describe for you today is going to be Z, or more precisely Z hat. And you can actually ask who is that. So when I showed the slide in the audience of Mike Friedman, he pointed out to me that this movie was apparently iconic movie of '88 or something, which is famous. I didn't know it's iconic, or it was chosen to be. And anyway, in any case, so the Z or Z hat that I'm going to discuss today is a gadget that was invented together with my distinguished collaborators. One of them is here in the audience. So some are physicists, or Du is half and half, and Ciprian is a mathematician colleague in LA. So there are many different papers, and I'll try to kind of summarize for you this development in a very informal way. So first, I was a little bit worried because normally when I give this type of talks, I usually focus on calculations, details, and I thought today in this talk I would prepare something which contains or tries to encompass algebraic structure of this new gadget. And given David's blessing in the beginning that this talk should be colloquial, I think now I'm fully justified. So from now on, I'll continue on the blackboard, and how do I erase this? Common suggestions. So the name of the game, again, is going to be this thing Z-hat, and my job is to slowly describe to you what it is. What it will aim to be is a functor, so it's a three-dimensional TQFT. Which tries to categorify WRT invariance of three manifolds. So that's a sense in which this is a new step or new direction that without safety net, that there is nothing to compare to. Why? Because in the categorification of knot invariance, you already have John's polynomial color Johns, which are written to you as a polynomial with integer coefficients. So the question is there something like that for three manifolds that comes morally from Chern-Simons theory or its close cousin, but has integer coefficients and can be written in terms of Q? So until recently, there was no such thing. And the goal of this object ZHAT or TQFT is to provide such a thing. So it's a functor that associates to a three-manifold a number, but this number depends on Q. So this invariant ZHAT of M3 is naturally a Q series or some function of Q. So to be more specific, it's Q to some delta, and then it's our series with integer coefficients. So that's a property. And to a two-manifold, it should naturally associate a vector space. So I don't know how to call it, either H, which is perhaps more suggestive if you think about some kind of Hilbert space. If you think about the functor, it's probably best to use the same uniform notation that has of sigma G. And one obvious question is, do we know this functor? So what can we say about it? So the goal of the talk in some sense is to say as much as we can about this functor. So that's what I mean by algebraic structure. We actually don't know if this functor extends further down. So obvious question is it extended TQFT? So that I don't know, and I'll try to emphasize everything that we do know and do not know about its algebraic properties. And even the level of Hilbert space, all the, in this T-type formulation going down one level, we know very well, mostly for genus equal to 1, which is going to be my main restriction in this talk. So luckily, at this point, it's known very well how to compute it for any three-manifold. So that's in some sense the goal of paper of Chypre and Manolescu recently that tries to build this Q-series for three-manifolds out of surgeries, because any three-manifold can be handled by surgeries or knots or links. This level is checkmark. This level is kind of partial checkmark only if I say that genus is 1. So we don't actually know very well how to do cutting and gluing along genus 2 surfaces and higher. So that would be natural generalization. And also extended structure is a question mark. So the goal is to construct such a TQFT. And again, normally if either I or many of my collaborators give talk on this, we focus on how to compute, because at first when this thing comes about, people ask you, okay, can you compute it for this manifold? Or can you compute it for hyperbolic surgery on some complicated knot? I don't think, well, this is hyperbolic, it has lots of surgery. So I think always when people ask this, it feels like they hope that the answer is no, that it's not computable or it's not defined. So now this is kind of check mark. So this can be done if you have a three-manifold that you really care about, such as surgery on this knot. Okay, there is a way to compute. So therefore, we don't have to worry about computations. But again, this is super nice and explicit. But I'll try to do something that we usually don't do. There is an algebraic structure behind this functor, which we also don't know, and which I believe is going to play an important role in trying to understand what is this thing. Is it extended TQFT? What these lower levels are based on? For example, is it a category associated to a circle? Since we don't know this, again, I'm going to throw myself into unknown and collect for you all the facts which are true, as much as we know about this thing, and will motivate some formulation of it that does involve, surprisingly, double affine Hecke algebra. Moreover, this formulation, to which I hope to get by the end of the talk, will combine this particular TQFT with some simpler, three-dimensional TQFT with some similar three-dimensional TQFTs, which are much nicer and easier to understand. So this DAHA somehow packages all of them together. So therefore, what I'll try to do, I'll organize the main part of this talk as kind of a summary of informal colloquial description of properties of this gadget. So we won't do computations or definitions. We'll just try to see from all past experience with knots, with other things, what could it be? What kind of properties it should have? And of course, I'm not wasting your time in the sense that a posteriori, they will all turn out to be correct. So these will be properties of this gadget. little clear?
You choose a Friday.
Oh, thank you very much. So this turns out to be, I don't know if it's extended TQFT, but it turns out to be decorated TQFT. So one of the surprises in the development of this thing turned out that you have to fix additional structure. So for example, by decorated TQFT, people sometimes mean spin TQFT and so on, where you have to fix a spin structure. So if you're not very familiar with such decorations, please ask Dan. So he'll tell you a lot about these decorated structures. And this theory turns out to be decorated TQFT in the sense that there is additional label, which actually is spin C structure on 3 manifold. So this came out as a surprise, and that plays analog of framing. That's it. Any other questions? Mm-hmm.
I assume this series just convert like zero radius of convergence. Is that correct?
That would be horrible. So that's one of the properties to which I get is if it's not really a function of Q, that would be really hard to work with. But it will be much nicer.
Because I mean, the Russian invariance is normally defined, they're very discontinuous.
Absolutely. So that's exactly the challenge. So that's why this question, is there some power series in Q or polynomial in Q that we can attach to a 3 manifold that's actually a Q series? So that was one biggest open question before even we categorify, before we have coefficients and their interpretation at some graded dimensions. Question was, what's this as a function of Q? And you're absolutely right. So there are several ways to do it or approaches that people try, and this is one of them. So it's still not kind of settled deal, but I'm trying to tell you a story that naturally emerges from physics. So from physics perspective, it's very, very similar to a story that you run for knots. So for example, you compute the invariant that you get, so this object Z hat for a 3 manifold is indeed sum over ij minus 1 to the I, 2 to the j, and then dimension of some doubly graded space hij, which you associate to 3 manifold, and in addition you have to pick this spin C structure. I won't worry about it for now, which is space of so-called BPS states. I don't want to describe that in great detail, but setup is really very, very similar for knots, so therefore this integrality will be kind of natural and manifest, and the setup involves a choice of 3 manifold cross a cylinder, which is, so this is a picture of R cross a disk, 2-dimensional disk, where you study some 3-dimensional n equals 2 theory called T of M3, and you fix certain boundary conditions on the boundary, but this thing is effectively quantum mechanics, so that's why the space of Hilbert space is just a space, and we can compute it using Gukov homology, and these are the groups which appear here. So my goal is to describe properties of it, not mathematically, not physically, but mathematically. And we'll again use all kinds of clues and hints from successes of this story, which was applied to knots, and that led to this kind of magic trick that I showed you earlier and various other developments, which is exactly similar. So we'll try to borrow some of this intuition.
Can I ask?
Yeah.
So last week we had a series of lecture about 2 constructions of Rosansky. Is this related to Kalana-Rosansky or Gukov?
So this is, I mean, there is Hovanov-Rosansky Homflick homology, where, in fact, motivated by this proposal that they constructed theory after Mikhail did SL2, SL3 case. And then there is also Hovanov-Rosansky SLN, so for fixed rank. So what I'm doing today is closer to fixed rank. So in fact, for today, let's fix choice of E algebra to be SL2 throughout. So that's going to be our default choice. So clues or hints. What can we borrow from knowledge of knots to make this work? First of all, you can ask, okay, I know that WRT invariants of three manifolds are closely related to invariants of knots. In particular, if you want to study surgery on a knot K, then you can compute corresponding three manifold invariants by taking that colored kind of John's polynomial that we saw of a knot K and summing over color. So that's roughly the structure of a surgery formula in WRT theory. So first thing in this H-hat business would be, well, this one. This is more like this space of DPS states assigned to a three manifold that is categorification of that hat. Natural statement would be, okay, we know all about colored homology and its categorification, so why don't we sum over color? Try to mimic the surgery formula, basically take sum over color of colored homology of the knot K, same kind of thing that I showed you in the very, very beginning. So this was a proposal that Cyprian suggested on the very first day of our collaboration, and morally, the result is that it kind of works, but details are interesting and complicated. So that's first thing you try to mimic, same sort of surgery formula. So what's interesting is, yes.
So here the color choice polynomial is a polynomial, right?
Yes.
Is it coming from a quantum group or something with the root of unity?
So we'll get to that. So of course, WRT invariant is at root of unity. And Color-Jones polynomial, when we categorify it, we want to have function of Q. So that's precisely the goal, to construct something that depends on Q, that has no reference to root of unity. And I'll talk about that in a little bit. That will be one of the other
Okay, but you don't want to say what it is on the right-hand side.
On the right-hand side, so my point is that on the right-hand side we know a lot. So we know, of course, this, all colored Joneses very easily, that's previous century. In this century we know colored homology that can be computed in many different ways now using kind of technology that we saw. So we know this. So question is, can we mimic surgery operations? If we know everything for knots, morally the structure, and again I'll try to be colloquial, I'll emphasize the structure, morally the surgery on a three manifold, on a knot, involves this. So if you know all of the groups, how would the answer look like? So
is that a direct sum or is it a filtration with that associated gradient?
At this level, it's just a direct sum, but how you do the sum, because there are more bells and whistles in this formula and correspondingly here. So again, I want to convey the punchline that it's morally quite right, but details are really complicated. So we're involved in a sense that you wouldn't guess them obviously. So you need many clues. This is going to be only one of many. But structure is somewhat similar. So second clue is another interesting fact, that individually this knot homologies, which are colored, so I should say that this is colored knot homology, were noticed to enjoy action of various algebraic structures, very simple or sometimes not so algebras. In physics, they emerge as algebras of, again, DPS states. And in knot theory, it was always kind of strange why they appeared. For example, Alexei, again, when we were both young, did a lot of work on this 10 years ago. And we were always excited about the appearance of some algebras acting on knot homology. And we saw that as you increase color, as it gets bigger and bigger, the structure actually comes to life in some sense. So that natural thing that happens here is we basically sum over all colors. You would expect that it should come to life even more because you package everything together. So natural question is that, is there bigger algebra acting on it? So it turns out, as a result of computing this object, it turns out to be a module of logarithmic vertex algebra, which does depend on the choice of three manifold, just like the algebraic structures that were seen here in old days depend on choice of knot. So for example, you change one porous knot from one to the other, the algebraic structure varies. So this is another kind of surprise. Not only this infinite homology of three manifold exists, it turns out to have a meaning, and it's nice and surprising fact. Therefore, this graded Euler characteristic that's written here on the board is nothing but a character of logarithmic vortex algebra as a function of Q. So that gives you a kind of hint of what answer we're looking for. It's going to be a Q series, and it's going to be a character of some vertex algebra, but it's not a nice character which enjoys nice modular properties. Logarithmic VOAs, which correspond or which have non-semi-simple tensor categories, have characters which are mock modular or even worse. So this is not a nice modular thing, but it's kind of spoiled modular thing. So therefore, that this always holds for any free manifold is a conjecture. I'll call it 3D modularity conjecture. That this invariant Z hat is in fact always a character of log VOA. In fact, among these algebraic structures that played a role in theory of knots,
Still for SL2, or you have.
I guess conjecture could be made for any SLN today. Let me restrict myself to SL2. Just so conjecture, of course, should be that it's for any SLN. So double affine Hecke algebra also played a role in case of knots. So it will show up here again, but that's another kind of clue if you think about algebraic structure.
You mean rational DAHA, right? Or what?
For us today, it will be actually full spherical DAHA, not rational. But in those days, there were different forms of DAHA, in fact, including your word.
Rational or just.
Today it will be spherical, non-rational. Spherical full DAHA. So I guess I'll save this kind of main wish list or main goal for now, and continue here on this side. I hope it's okay. So I'm down to number 3. So the reason this magic trick worked is that this Hopefully homology that I showed you comes equipped with a very rich structure of differentials. I used only 2 of them, and again, if I have a tough question like how do you reconstruct these diamonds and everything else, I can use more than 2, but for magic trick, usually 2 is enough if you restrict to knots up to 10 crossings, which gives rise to spectral sequences on homological invariants of knots, which allow you to relate homology for SLN when n is sufficiently large. That becomes very cool and closer to Hopefully homology. And some homology for same node, but smaller group, or in general some SLN/M supergroup, where super rank n minus m is much smaller than original one. So this works very well in the world of knots, and again, this is a really interesting structure. In fact, such differentials are part of this algebraic structure that many people observed and studied, and it was a lot of fun. So you can ask, if it comes from the same origin, from the same physical system, why not expect the same for 3 manifold? So naively, I would think that this is totally outlandish, but surprisingly, this is seems to be close to correct. And again, here I'm presenting kind of aspects which have not been explored. So I'm stepping into this unknown, describing properties of this object, which again is very concrete, but I'm trying to tell you what's usually not written in papers. So something that's how we think about it nevertheless. So in particular, in the world of knots, there was very special, interesting case where n is equal to m equals 1, and this would be what's known Figure-Fleur homology HFK of a knot K. And its analog for 3 manifolds is the only homological invariance of 3 manifolds which exists mathematically at the present day. It's called Figure-Fleur homology. So when n is equal to m equals 1, it's called HF plus of a 3 manifold. And therefore you can wonder if again, there are such spectral
So
sequences.
what about Witten-Richtich and Tureyev? So we have.
What vector
You
space?
claim that is the only invariant.
No, homological. Homological.
Homological.
If you know another one, tell me, because it's going to be or interesting one which comes from quantum. So that's the only one. But already here there is something interesting that if you think about it, this homology actually depends on a choice of spin C structure on the three manifold. So if such spectral sequences or differentials expand to the world of three manifolds to the same kind of TQFT, which has not as defects but allows to work on general three manifold, we better decorate it with this label A, which keeps track of spin C structures. So that's another clue or hint if you know nothing about, again, inner workings or detail. And surprisingly, first of all, such spectral sequences do check out in the case of three manifold, which is a three sphere. So Pavel showed me how it works, and I was really surprised. So, but again, probably you shouldn't, because it's the same type of package. And I was even more surprised indeed when this A's, this spin C structures showed up. So they show up in different ways. This is one way to motivate them from such spectral sequences. The way it naturally appears is also through abelian flat connections, because the set of spin C structures on a three manifold can be identified non-canonically with H1, or torsion part of it, of three manifold. Okay. So it looks like this label A takes values in the moduli space of abelian flat connections on a three manifold. So that's the sense in which this TQFT is actually decorated TQFT. So in particular, when you do cutting and gluing, you have to keep track of how this spin C structure or this label A gets cut and glued. So that's another interesting clue.
Who's that space? M flat?
M flat abelian. So I have to make it more precise. What do I mean? So if I think about U1, that's the natural way to think about this isomorphism. But our theory is not U1. It was SU2 if group is compact, or SL2C if it's complexified. So in terms of, so what I'm going to correct next is make it SL2C flat connections and put abelian here. So that's actually the way to think about it. And this will suggest generalization to higher ranks, where if you want to study SLN, this label A will take values in abelian SLNC flat connection. So they will be basically replication and times divided by the while group.
Abelian flat connection, you mean the
One.
monodromy is contained in some common proton?
Yes, exactly. So for SL2, for example, one nice thing is that reducible and abelian is the same thing. So but things will get actually much more interesting in higher rank. Okay, so these are, again, some very limited partial clues. I'm basically collecting small nuggets wherever we can find them in whole story, especially based on knots. But hopefully they already start kind of fitting together, and I never gave a talk where I'll put all of them on the same blackboard, so I think if you do this, you get a picture of what this gadget looks like. So now we already start talking about this moduli spaces of flat connections. So another next clue, which again was mostly motivated by knots, but now this makes a step toward three manifolds, is something that also was done in late 90s and so on, the volume conjecture and its various generalizations. Which tells you the following, that if you want to study generic values of Q, so Q is going to be inside unit disk, absolute value less than 1, I'm thinking somewhere here, then what you effectively have to do is to replace SU2 gauge group in Trent-Simons theory by SL2C. It's complexification. So if you want to do generic Q, you lose the level. You don't have K anymore. You cannot talk about integrable representations of affine cut smoothie at a fixed level. And instead of finitely many of them, you now get infinitely many. And the way to think about them is that you're working a generic Q, and your quantum group, which for me will be Q of SL2, is a generic Q inside the unit. So that's kind of another clue how we should start thinking about this thing. And now, natural question is, okay, if that's generic story, that this functor Z hat is trying to deal, how should it be related to Witten-Rischetichen Thorive invariant? Obviously, it should be related by taking Q to be a root of unity, so you should expect that as Q goes to exponential of 2 pi I over integer, K, the usual level, then you find that this value as a limit, WRT invariant of that same 3-manifold at level K. So that's the goal.
There are also some expectations what happens when Q goes to 8 point in the circle but not a generic point.
No, expectation is that this Q series will actually diverge. So the goal of many of these papers, including the one with Chyprian, is construct explicitly this Q series. And again, normally I'll focus just on that. And some people in the audience already saw various talks of my collaborators on this. So it's a very concrete Q series, and you can play with this. So I don't think it's being studied exhaustively, but from playing with it, people saw that it behaves really nicely at rational points on unit circle. But the generic irrational point will be.
Do you expect that there will be some modular analog of it on the generic point? Like we check in the TQFTs?
I don't know.
Because have Q differential of some exotic, rather complicated modular function. So it is involved business, even for a torus like 2 plane plus 1. Right?
Well, this is for 3-manifold. So, but I think it would be good to study it. Again, I don't know. All I know is that it turns out to be, for example, character of log DOA, and therefore question is equivalent to asking how characters of log DOA behave. But there are many concrete expressions. For instance, if you want later, I can show, I don't know, some examples or even example of 3-manifold.
Could you say that again? What you're looking at some class of representations for UQSL2 like this. So you wrote UQSL2 on the board and you put this condition that Q is less than 1. What do you do with UQSL2?
So at this level, I don't know. So that's why it would be good to have this understanding. So that's why I'm kind of presenting it here. But I can tell you what we roughly would expect. So especially if you take, say, Q2 to be root of unity. So let me motivate it by the following. So here I'm talking about right. So
Can you repeat again what is the statement about the root of unity?
So the statement about root of unity is that there is a precise relation to WRT invariant, which roughly says, very roughly again, with the same level of sketching as I do for everything else, that if you take limit of this Q series at root of unity, you recover WRT. So limiting value at roots of unity, radial limits, should give you WRT. But we should suspect that this is delicate, and indeed in practice it is, because of the following. If you take this tensor category of quantum group and take the limit to be root of unity, we get not exactly Berlin function. We get that before semi-simplification. So there is this additional step, which semi-simplification, which relates then most obvious limit and then you're covering WRT. So I want to motivate it by, or asking how it should be related to WRT by showing something like that. And it will be, again, made more precise a little bit later. Suppose you think about principal series representation of SL2.
So why is it important that the absolute value is smaller than 1 on that level? I mean, I understand it in the volume conjecture, but why is it?
Yeah, in many places like volume conjecture and physics setup, it's natural boundary. So, and all of these Q series that had turned out to be defined only in that unit disk. For example, Theo was asking, why isn't it have 0 radius of convergence. For some reason, it happens radius 1. Again, I don't have further deep reasons, but several facts point to that. And the answer turns out to have all these properties I mixed. So think about principal series representation of SL2. It's an infinite dimensional representation. So if I think about Cartan types, there are all integer points on a line for SL2, where I have raising and lowering operators E and F. And if I think about orbit method, this is basically projection of non-compact orbit that corresponds to principal series of SL2R on this line. Now, this is generic case. Think about this as being analog of generic Q. If you vary parameters, principal series representation of SL2 may exhibit the following behavior where some of these raising and lowering operators will kill your vector. So you'll get 0. So you'll get stuck, for example, at this point, or it may equally get stuck at this point. So the picture of the orbit, in the orbit method, that represents this, is that you have something like this.
So it is very much different story versus modular and unimodular QT, right? This is just, we say it, this is real case, this is compact case, right? This is, from the harmonic analysis, you switch to something else, right?
Well, from the viewpoint of harmonic analysis, I'm talking about, again, orbit method and forms for...
We cannot expect connection with mod Q equals...
Oh, no. I'm just motivating. I'm trying to draw a parallel which will be more precise, but this is easier setting, so I hope more people are familiar with this so far. What should be the parallel? That for special values of parameters, when you have resonance conditions, your raising and lower operators can hit E and F, can hit boundary, and therefore you get, for example, finite dimensional representation and, say, discrete series D plus and D minus. And what you typically get in such instances is extensions where you have, so you can think at this point, principal series representation can be viewed as an extension of V1 and V2. So if I'm interested in V, if that can be constructed as an extension of 2 other guys, where in this picture, for instance, this can be V1 and this can be viewed as V2. But what I'm trying to illustrate is that in this familiar setting of SL2 representation theory, there is subrepresentation, this finite dimensional discrete guy, which sees as a piece subrepresentation on something much bigger at a very special value of parameters. So relation to WRT invariance on the setting should be such that there is a representation of SL2Z, which is infinite dimensional. It's a Grothendieck group of some tensor category for generic value of Q. And when you hit resonance condition, such as root of unity, it spits out your linear representation, which sits inside. So that's what we should expect.
Did you say SL2Z or SL2C?
So now I said actually SL2Z, maybe for the first time, that there is infinite dimensional representation V for generic value of Q, which is Grothendieck group of some modular tensor category, such that if you hit resonance condition, when Q becomes non-generic, it contains subrepresentation, which is WRT over linear. So that's also what we expect from this picture.
But you don't mean mod. I mean, you said it was an infinite dimensional representation of SL2Z that was a Grothendieck group of a modular tensor category. Right? The modular tensor category has a finite.
Right, exactly. So I'm using this modular tensor category in a loose sense. Exactly. So it's analog of it, but in an infinite dimensional setting. So I'm actually deviating from Katerina's talk today in 2 different ways, and both on point. A, this will be infinite dimensional, and B, it won't be semi-simple even if I try to take root of unity on the nose. And both are cool and interesting. And again, non-semi-simple tensor categories are representation categories of these log DOAs. So we start gradually seeing this network of facts forming. Yeah.
Where does SL2Z?
Good. At this point, it comes from the fact that if you want to, right, so I'm implicitly using a theorem of Turaev, which roughly speaking says that if you want to build a 3D TQFT, let's say for now traditional and usual one, then 3D TQFTs are in correspondence with modular tensor categories. And in fact, here I really mean modular tensor category and that without relaxing any constraints. So this is basically the category that you would associate to a circle in the T type formulation of a TQFT. And vice versa, if you have modular tensor category, Thrive tells you how to construct a 3D TQFT functor, where the crucial thing is cutting and gluing along tori. So SL2Z comes as mapping class group of a torus. So I barely raise this thing, but the point is that if you have this functor for genus G Riemann surface, such as genus 1, then the important thing is that on this Hilbert space, you should expect action of the mapping class group of sigma G equals 1 in my talk, and that's actually SL2Z. So therefore, from now on, the rest of the talk is going to shift focus to SL2Z. So building 3D TQFTs, what I want to say, is very, to that process, is very important to have SL2Z representation. These are graph-in-D groups of some categories, maybe not MTCs in strict sense, but with some relaxed conditions, especially when we have infinitely many systems.
Just a simple minor question. So this SL2Z action on torus, it's something like the twisting of around the cycle when you do the sources together.
Exactly. So that's actually what I want to emphasize, is that that aspect is a critical part of building 3D TQFT. Yes.
How do you see A on the torus?
This stage. I didn't. In fact, when it first came about, I resisted to put my name on a paper saying that this is nonsense, that this A is fluke, is incorrect. My collaborators convinced me that this is right. So I'm among all the people I listed in the beginning, least experienced with A, what it should be. But now I can say that it's a relative spin C structure. And in fact, this is something you learn from your papers. But,
what is relative? Relative
relative when you do cutting and gluing, like Dane twist on a torus. So you define it on a 3-manifold, but then you ask how it is compatible with the spin.
Still A is connected with 20-fold geometrically, but
no, that's a different A. So your A is a continuous parameter. See, this A takes values in a discrete set, which is roughly torsion of H1 or spin C structure.
Are you sure that this A has geometric meaning in terms of the elliptic curve, in terms of the torus?
No, I think it doesn't. My point is that it's spin C structure.
Maybe you were right long ago when you suspected that this is not
No, I suspect a lot of things, but this one is really good.
So, Sergei, are you going to give us a new representation of SL2Z, one that
Yes.
works for arbitrary cube?
Yeah. So
is it finite dimensional? What's
no,
its dimension?
I'll give you. So that's the goal of the talk to answer this. In fact, the name new 3D TQFTs from DAHA is basically trying to capitalize on this idea very seriously. So I'll get to that. So that's exactly my punchline. Right. So I have one more clue from old days, like what shall we expect of this functor Z hat as far as algebraic structure. And aside from that, I really don't know. So therefore, what I want to say is that really, if anybody has ideas, thoughts, how to make this in a more complete picture, please write papers or talk to us or do both. And I'll proceed after that to just giving you now answers or what it is. So it's much easier for me to give answer than to say from what algebraic structure it comes. And I really tried my best. I apologize if I cannot say more at the moment, partly because this functor is constructed only at the top levels. But that's already good enough because especially once you do cutting and gluing along tori, so this is where this Tori's theorem comes from, you already start seeing something. And in this recent paper with Chyprian, where we gave a general gluing construction along tori, you're required to have this for gluing knot complements. You notice that in this Hilbert space for genus 1, so first of all, it's infinite dimensional, and it's easy to construct this Hilbert space abstractly, but you want to describe not just the SL2Z action, which is mapping class group action, but also norms and lots of other things. That's where the story gets really delicate and interesting. But we notice, so this is from GM, that it has a basis, which is basically basis of states, both of labeled by M and M, and also A. So A again has to do with the spin C structure, but the most important point is that there is this N and M pairs of integers, which should be thought, modulo while group, as character and co-character lattice elements divided by the wild group. And proposal is that that's going to be generic. So this is one place where you start seeing deviation from, say, WRT. In WRT, when you write an S matrix, elements as lambda mu, like Katerina did earlier today, lambda and mu take values in just root lattice or weight lattice divided with this cutoff imposed by k, by the level, but they take values in just one copy of lambda. And here there are two. So therefore, what you see, what this clue tells us, is that we're talking about some toroidal or double affine where states should be labeled by pairs of such. That's another clue or another surprise. Okay, so now I'll come to giving the answer for how to construct such things. So this is, most of the talk was, first part was entertaining. This is kind of bunch of clues which are useful mostly probably for experts who have intuition for them. But then last 10 minutes is again just something more elementary or more concrete. So I try to emphasize the role of SL2Z and how do you construct interesting TQFTs. So one way, which I never saw written in this form anywhere, but from clues I gave you, it should be extremely natural, is to ask for algebra which has SL2Z action from the start. And now you see why dot. Or for me it will be spherical dot. Suppose, so this is algebra. Suppose you have representation V of that algebra. What you want is that SL2Z also acts on V, doesn't permute it with anything else. In other words, that is compatible with algebra action. And that's the first starting point. Moreover, in every setting, so I'll give you a short table by the end of this 10 minutes, where in each case, this representation of SL2Z, be it finite dimensional or infinite dimensional, E is going to be Grothendieck group of, I'll put it in quotes, MTC with possibly relaxed conditions. If it's finite dimensional and unitary, everything is nice, but sometimes you have to relax something. And from this point of view, modularity should be clear and important, because M stands for mod.
And should we think that the SL2Z action is the one induced by the action?
Yes, exactly. So that's in some sense the key point of this talk. So this way of thinking or constructing SL2Z representations, and then you want to think of them as generalizing Drive's theorem, typicalizing on the SL2Z action. You want to think about this SL2Z as mapping class group action when you cut and glue along toral boundaries, and then you're done. So that's it.
SL2Z or is going to be a finite index subgroup? Because I have the feeling you want to switch lambda and lambda check at some point.
It could possibly be, we haven't seen it yet, but that's a great comment. So in fact, if it shows up, we should be alerted to this, absolutely. That's a very good comment. So far we're doing SL2, so maybe factories of 2 will show up and sometimes they do, so that's a good point. So it's better yet if, so this is abstract, not algebraic construction. It's better yet if you have construction of this algebra and representation as in some geometric way. So suppose you have some kind of A model or B model where you have either Fukaya category or derived category of coherent sheaves on some target space Y. Then you can take objects in this category and construct algebra as self-home of a certain object. I'm going to call it BCC. So this will be object, physicists would call it brain, in either derived category of coherent sheaf on some target Y, or in Fukaya category, also derived version of that on Y. Sometimes you can have both, especially if Y happens to be a hypercredit structure. So in that case, you can actually give sometimes both descriptions. And if you have such construction of algebra, you can construct representation by taking form of this BCC object with some other object. And from geometric point of view, what's important now, in order to have this SL2Z actions, is that both BCC and B prime will be fixed by SL2Z, but not necessarily pointwise.
So this is just internally the morphism of an N object.
Yeah, exactly. That's the algebra of N morphisms, and this is now representation. So string theorists like to draw this Venn diagrams, which illustrate why the action is. I don't want to use my time, so I won't go. So these guys are now fixed by SL2Z, but not pointwise. If I think of them, say, as Lagrangian supported somewhere, for instance, then it's very geometric. And of course, in that setting, it's natural to ask that SL2Z also acts on the target.
So action of SL2Z and capture.
Yeah, exactly. So for me, so this construction naturally gives an algebra. So if BCC is a rather specific object, which indeed happens in this hyperscalar setting, then this algebra is can be shown to be isomorphic to deformation quantization of Y, the target space. And from now on, I'll take
some target.
Yeah, Y is the target space. And to finish the talk, I'll take Y to be a cubic surface, XYZ minus, or rather, plus x squared y squared z squared equals 2 plus t to the minus 2 plus t squared, which is also, so this is hypersurface in C3. It enjoys beautiful SL2Z action by algebraic automorphisms, which play a role in dynamical systems and so on. But for us, this is moduli space. This is moduli space of SL2C flat connections on a punctured torus. Yeah. Or in the puncture, you insert parameter t, labeled bit. Okay, so it fits perfectly this setting. It gives algebra, which in this case is deformation quantization of algebra functions of x, z, and y. And theorem of Alexei shows that Gukov.
I think it's theorem of Cayley. That's
that algebra in this setting is spherical double affine Hecke algebra, which does enjoy SL2Z, so that's important. And therefore, we can try to start playing with it. Now,
invariant connections. Otherwise, it is just DAHA without spherical, without the spherical. You know, it is definition, literal definition of DAHA, but you need to impose quadratic equation for half a term here, right? And then it will be exactly definition of DAHA, but non-spherical. Right?
Well, if I understand correctly, this deformation quantization gives spherical DAHA, right? So I have experts in front of me, so I shouldn't say something
that connection, but invariant flat connection, something like this. Right?
That's what he means by the T. So he means that the monodromy around the puncture has is in the Reiner-Smith.
Then it is DAHA non-spherical DAHA, the full DAHA. Definition. This is the definition of DAHA.
Spherical DAHA.
From what I'm told, it's spherical DAHA.
And your Q and T and your DAHA.
Generic. At this point, generic. This is monodromy of SL2 connection, eigenvalues. So this, in fact, was written here as a trace of that monodromy as a local system. And Q comes in quantization. So Q in this story is always exponential of H bar. But here Q is again generic as a prime. So now it has all the properties I mentioned. And the game is going to be what V's, what SL2Z representations of spherical DAHA carry. Sorry, what representations of spherical DAHA also carry SL2Z action. So that's going to be the application of it. And there are several natural candidates because in the present setting, if I take this to be my hypersurface, it's H2, the mid-dimensional homology. So BCC is some line bundle. So this is going to be line bundle on a target space. Sometimes it's called pre-quantum line bundle. on Y. And the important thing, so that's not terribly important, what's what we choose for B prime, because this will give us different representations. So this is 5-dimensional, and intersection form on H2 is basically a fine linking diagram of D4, so it looks like this. It has one component in the middle, to which I'll give a name bond G, for reasons that many people here can explain better than I. And it has a couple of brothers and sisters attached to it, which arise by deforming from T equals 1, in which case this would be blown down, and you can think of them as exceptional divisors, D1, D2, D3, and D4.
Sorry, this is a picture of what?
This is a picture of
White space, right?
compact piece or to which this hypersurface retracts. So it consists of what's called pillowcase, basically 2 torus divided by Z2, which has 4 C2 mod Z2 orbital points, which if you blow up, and that's what parameter T does, produce for you space to which this hypersurface retracts. So now, given what I said, the natural question is which of these different choices are fixed by a SL2Z action. So this is last thing I want to tell you.
So the story that you're telling us should work for knots as well as for free manifolds. Is that
Correct, correct. So it should combine both knots and free manifold in the same
So you're
way.
predicting a new computation block as well.
Well, in that case, it will reduce to previous computations
How do you know
from. Well, we checked. So, for example, in this joint paper with you, Pavel, and so on, it basically it's the same physical system, so it boils down quickly to the same thing. But goal is to again free manifold, to incorporate free manifold. So I'm out of time. So I'm actually done. Perfect. So there were some questions, so I apologize for using extra couple of minutes. But last thing is to give you a table to summarize what do we get out of this DAHA, and now connect it to all these clues that we're trying to collect along the way. So the table is going to be long but very thin. So first I'll ask, what is V? What is the representation of spherical DAHA that we'll use? V is such that it enjoys SL2Z action. So that's going to be the first column on the table. Second column will be corresponding object. Here, since I'm finishing up, I can be very cavalier and even call it brain, not even say object in the category, but think of it as Lagrangian in the Foucault category, or find it some object in the derived category of Coherent sheaves on Y, on this hypersurface. So then I'll tell you condition which is required for this object or SL2Z representation to exist in terms of Q and T. And then I'll tell you dimension of that representation of SL2Z that emerges. Sorry, this is dimension of V. Dimension of V. Then I'll tell you corresponding TQFT. And MTC encodes again that corresponding undertaking. So in rank 2, I mean for SL2 there is not much luckily. And they're all interesting. And they realize all the clues that I mentioned earlier. So first, we believe that there is interesting functional representation, or we believe that the one we need is what Vanya calls functional representation of spherical DAHA. I actually don't quite know what the right brain is. We have various candidates and people.
What is functional?
I'm out of time, so I want to finish with the table, but no, that's if I understand correctly, I don't want to put words in Vanya's mouth, but I think it's close cousin of polynomial representation.
Not polynomial.
Not polynomial, right? But it's defined using polynomial representation.
Some in delta functions. Right?
Yes.
So pre-representation in delta functions. Right?
Yeah.
Dual.
So I don't know what the brain is in this language, but again, we have some thoughts and would love if people give us thoughts and suggestions. Condition that I want to take it on is T equals 1, but it doesn't have to be. But the interesting thing is it gives you infinite dimensional representation such that it enjoys SL2Z action, and that's precisely where you have this TQFTs at hat, which S and T matrices of SL2Z action become S and T matrices that we see in paper with G-prime. So that's the statement. Now,
And the last column?
last column, well, it's basically this infinite dimensional S and T matrices, but I have to.
But what's the level of the logarithmic VOA?
I don't actually know how it's connected to log VOA, so it's probably related. But again, many things I said today are expectations that I don't know how we'll feel. So that's one of them. So then,
But what does it mean to have an infinite dimensional representation? What does it look like? How do they plot it?
So that's actually the most interesting question. So not so much how SL2Z acts, because matrix elements are finite dimensional. I mean, these are numbers, but how to take exactly how to multiply, how to take traces and products. That's
what
the
does
most.
it mean if you have a representation of SL2Z if you don't know how to take products?
Well, luckily we do. So that would be yet another talk. So claim is that that's exactly what paper with G-prime actually said. So that's indeed the beef of it. Not so much the S and T matrices, but how to take traces and products.
And that is known.
And
I think we should say further dimensions for private dimensions.
You need to explain.
So what I chose for this talk today is, among these different options, is the easiest one. So I have two more layers on this table, and thank you for helping me to finish it up. So
He's very tall.
So next one is going to be additional series representation, such that it comes from this central component bungee. So here I can tell you what the Lagrangian.
You mean my terminology? I just know something else.
Your terminology, yes, your terminology. So condition is also in your. By the way, in your notations, thank you. That's a really good question. Is t square is -2 to the minus n. Dimension is n+1. The TQFT is Rishiti into right, or WRT. And this is Verlinde MTC, and this is a piece. It's special values of parameters because this can be generalized functional representation, can be a generic QMT. So it sits as a piece in the bigger one just as we wanted. So that was one of the clues from the beginning.
So the theorem is really deforms Verlinde, exactly this particular
Exactly.
way.
Yeah. So that's precisely what we like.
You mean IMR and paper, right?
How many hours do I have? So, last one. You asked, okay, so this bungee has a special feature, just like functional guy, that it's fixed by SL2Z, but not point-wise. You can ask, how about these other fellows? It turns out that these three, D3, D4, D2, are permuted, so they form three-dimensional of SL2 representation of SL2Z, just like two torsion points on an elliptic curve. And this D1 is fixed. But again, not point-wise. That's an interesting statement. So another candidate, therefore, is D1, 1 out of 4 guys. I actually don't know the name for the corresponding representation, but I know its dimension. If t square, so it only exists if t square is 2 to the minus 12 minus 1. Its dimension is L. So this home is easy to compute. It's going to be L dimensional. You can compute it using Grafton, Dikrim, and Rochen.
So it is multiplicative Delin-Simpson from the same paper. Multiplicative, the story about multiplicative.
I have no idea. We should.
This is C check C1. If you were to be absolutely exact, what you're discussing is not A1. C check C1.
So the name for this, or what's?
Multiplicative Delin-Simpson, exactly. Of type D4.
Multiplicative Delin-Simpson.
D4 multiplicative Delin-Simpson. Just 1 to 1. 1 to 1. There is nothing really new.
So the corresponding TQFT is actually interesting. So you find this if you perform topological twist of so-called Argyris-Douglas theory, 4-dimensional theory, so this is a 4-dimensional theory, but you can study it on S1 cross a 3 manifold and ask how does it behave as a TQFT on a 3 manifold. And that's the one you're going to find here. Now, it has corresponding MTC, which is non-unitary. So here it's finite dimensional, so it has finitely many semi-simple objects, but it's non-unitary. In particular, you find that it's 2, 2L plus 1 minimal model MTC, the first of which for L equals 1 is going to be, or L equals 2 is Lee Young model. But it's not just that, it comes in a package. So here, it comes in a package with Fibonacci MTC and corresponding close cousin TQFT, which is obtained by acting with a Galois group of Q adjoint now 2L plus 1 root of unity, exponential of 2 pi I over 2L plus 1 over Q. And this is a completely different kind of different TQFTs, and some of them are obviously new, so that's the title of the talk. The second part with the same title, and much more understandable than mine, will be by Duque, because I believe his focus will be on finite dimensional ones. So my difficulty and most of the problem...
Wait, which is finite dimensional? You're discussing finite dimensional or what?
So the first line is infinite dimensional. And it contains, in the same way as a principal series of SL2R contains, say, discrete series and so on, pieces which are much better behaved, and these are finite dimensional ones. But they can be also produced from spherical DAHA by a mechanism which I didn't describe, but I will tell you more about later. So sorry about running over.
Could I correct one confusion? So, theorem of Cayley is that equality on top of here.
Yeah, since you did it.
Yeah, sorry, I confused
you on doing it.
So it's a cop. Yeah. This is Cayley 19th century. So that's
19th, 19th, right?
the 19th century. That's what I think.
Okay, so we'll have a coffee break and then let's start again.